You have learned a lot of laws already for the gas laws. You've learned Boyle's law, um, Guy-Luce's law, and so on, and Charles' law, and the combined gas law, and the ideal gas law as well. There's one more law that you're going to learn, and it's called Dalton's Law. Dalton's Law is the easiest of all the laws. It says that the total pressure in a container is the sum of all the pressures of each gas. Okay? For example, if this is gas A, and all these gas molecules exert a pressure of 5 atm, gas B, the yellow dots, exert a pressure of 5 atm, gas C exert a pressure of 5 atm. Of course, those numbers could be different, but in this case, it's just the same. The total pressure, when you combine all those gases into this container, would be equal to P total. It would be equal to the pressure of A, which is 5 atm, the pressure of B, which is 5 atm, the pressure of C, which is 5 atm. So the total pressure is 15 atm. Very simple. Okay, so the formula looks like this. P total equals pressure of A plus pressure of B plus pressure of C. And if you had more gases, you just keep adding. And that's called P total. The P sub A stands for partial pressure due to gas A. It's partially because there's other gases in there. PB would be the partial pressure due to gas B, and so on. Okay? So here's an example. There's also something called mole fraction. Okay? So the mole fraction looks like this. So if I have, in this balloon, I have 3 moles of A, and I have 2 moles of B. I have 5 moles of C. Find the mole fraction of A, for example. Find the mole fraction of each substance. So the mole fraction formula is, the symbol for mole fraction is this idolized X that looks like that. Sub A means the mole fraction of A. So the mole fraction of A would be, well, there are 3 moles of A divided by the total, which is 10 is the total, 10 moles total, over 10. So 3 divided by 10 is 0.3. This is the mole fraction of A, 0.3. And of course, please keep it in a fraction form because it's a fraction, not a percent. The mole fraction of B would be, go ahead and pause the video and do it yourself. It would be 2 moles divided by 10 moles, which is equal to 0.2. There would be no units. This is the mole fraction of B. And of course, mole fraction of C would be 5 moles over 10 moles equals 0.5 is equal to the mole fraction of C. Notice the mole fractions should all add up to 1, just like percentages add up to 100. Okay? So, if the partial pressure, if the total pressure inside the balloon is 1 atm, let's say that all of this is exerting a pressure of 1 atm. So all the A's are hitting the sides of the container, right, exerting pressure. All the B's are hitting the sides of the container, exerting pressure. And also all the C's. C, there's 5 of them. Not necessarily 5, but 5 moles of them, okay? I can't just draw 5 moles. Okay, all of those together are exerting a pressure of 1 atm. Okay, if the total pressure inside the balloon is 1 atm, what is the partial pressure of each gas? Okay, well, if the total pressure is 1 atm, right, and A is 0.3 of that 1 atm, that's the mole fraction, then the pressure of A would be 0.3 atm. Okay, so what I've taught you is this is called the partial pressure due to A. To get the partial pressure due to A, you get the mole fraction of A, in this case it's 0.3, and you multiply it by the P total. This is the total pressure. Okay, so this is the formula for getting the partial pressure. So the A can change to B. So if we wanted to get the partial pressure of B, then we would do partial pressure of B is equal to the mole fraction of B times the P total. So it would be mole fraction of B would be 0.2 from this formula here. P total would be 1 atm. So it would be 0.2 atm. So this is the partial pressure due to the molecule B. Okay, and the partial pressure due to C would then be 0.5 times, that's the mole fraction, times 1 atm is equal to 0.5 atm. So what does this all mean? It means that if you have a balloon and it is 0.3 of A, it will exert 0.3 of the pressure. If you have a balloon that has 0.2 moles of B, it'll exert 0.2 of the pressure, which makes sense because it's 0.2 of the molecules in there. Okay? So the formula is up here. The partial pressure of something is equal to the total pressure times the mole fraction of that substance. Okay, the reason we're doing this is because in the lab, when we make a gas, we have to mix it with something else, and I'll show you what I mean. Okay, first, let's look at water vapor pressure. So, you know what water is. It's H2O. H-O-H. Okay. Because there's energy in the room right now that you're standing is about 20 degrees Celsius, some of those water molecules will go from liquid to gas. The gas water molecule is still H2O, but they're just farther apart from each other and there are no IMFs. And that water molecules right here are hitting the sides of the container, exerting pressure. That is called water vapor. Vapor means gas, and it's exerting pressure. It's hitting the sides of the container. Okay? Over here, it's cold. The temperature in the room is cold. Let's say the air conditioning is on, and over here, it's hot. What can you say about the water vapor pressure from cold to hot? Of course, the water vapor pressure increases because the energy of the molecules is higher and it goes into gas. So if you look at this chart, as it gets hotter and hotter and hotter, the pressure due to the water molecules in millimeters of mercury goes higher and higher and higher. Makes sense because there's more energy. As it gets hotter and hotter and hotter, over here, 55 to 100 degrees Celsius, the pressure gets higher. Okay? Now, when you hit 100 degrees Celsius, this is what happens. So here's your water. In the liquid phase down here, that's water. And in the gas phase, okay? When you hit 100 degrees Celsius, the pressure that this water molecule exerts is 760 millimeters of mercury. 760 millimeters of mercury of water vapor pressure. That's H2O, okay? If you are at sea level, let's see, you're at sea level and you're boiling the water and you're heating up the water to 100 degrees Celsius, what happens is at sea level, there are some oxygen molecules, nitrogen molecules. It's called atmospheric pressure. At sea level, there is 1 atm of atmospheric pressure, which is equal to 760 millimeters of mercury of air molecules. Okay. And these air molecules are pushing down on the water, preventing it from boiling. Because at 100 degrees, you also have 760 pushing against it, your water starts to boil. And that's why water boils at 100. Okay? What is the boiling point of water? 100 degrees Celsius. Why does it boil at that temperature? Because there's enough water vapor pressure to overcome the atmospheric pressure and it boils. Okay? And of course, that is at sea level. If you go on top of a mountain, you can make it boil at a different temperature because the atmospheric pressure is different. Okay? Now, in the lab, we will be collecting a gas by bubbling it over water. So let's say you're doing a chemical reaction and you're producing hydrogen gas. I'm sorry, H2 goes down here. Where's that? Okay? If you're making hydrogen gas, you can't just trap it, right? You have to put it into a container. What we do is we bubble it through a vessel, let's say it's a jar filled with water, and this is the H2 gas in there. Once we collect it, we can get the volume of that to plug into PV equals nRT. We can solve for the temperature. The temperature is just temperature in the room. We can get the pressure somehow, and so on. We can study it. PV and RT. We can get all those once we collect it. Okay? But the problem is when we collect hydrogen gas in here at 20 degrees Celsius, there are some of these water molecules going up because there is water vapor pressure, right? So some of these water molecules go up, so now your gas is not just H2, it also has some H2O. Your gas that you collected is wet. The problem is when collecting a gas over water, the gas you have collected is wet. There are water molecules in it. Therefore, you must subtract the water molecules from the total. You have to take the water away, subtract it to get the pressure of your gas to plug it into PV equals nRT. Okay, so how do we do that? This is what we do. So here's a scenario. You collected hydrogen gas over water. Okay, the pressure reading that day is 760. So what you did, and the temperature of the room is 20. Okay, so this is what you did. So this is you collecting your gas, and it's in a tub of water because of course you can't collect it over anything. It has to be water. So there's water right there. And your gas is in here, H2 gas, and there's also some water vapor. Okay? The pressure reading that day is 760, which means the pressure outside from the atmospheric gases is 760. Okay, millimeters of mercury. So you have to measure that in the lab. If you make the water levels equal to each other, if you add this together, the pressure inside will be equal to the pressure outside, so the total pressure is also 760 mmHg. If you make the water levels equal. All you have to do now is subtract the water away. So your temperature in the room is 20 degrees. How much water vapor is in there? There is 17.5 millimeters of mercury. So all you have to do is, if this is 17.5 millimeters of mercury, you have to subtract that from 760. Okay, so 760 minus 17.5 is 760 minus 17.5 is equal to 742. So your pressure of your gas is 742.5 millimeters of mercury. Okay, so what you did is you just found how much pressure is due to the hydrogen gas. Well, your hydrogen gas has a pressure, that's the partial pressure due to hydrogen gas, is equal to 742.5 millimeters of mercury. Now that you know that, you can plug it into PV equals nRT. You know your temperature in the room. You can measure the volume by the tick marks in the glass. Now you can figure out how many moles of gas. which is pretty amazing because you can't see the gas molecules, you can't even weigh it because it's too light, but now you can know the moles, which you can then convert to grams.